whenever you want.
Yeah. Thanks for the kind invitation and kind introduction. So today I'll present my talk on grand unified theories and its prediction of proton decay, topological defects, and the effect of inflation and production of gravitational wave from topological defects like cosmic string. So I'll talk, my talk will be based on a few of our publications in collaboration with several people. As you can see their names here. So let's get started. So here are the publications we will follow in this talk. So here is the brief outline of my talk. So I'll first try to introduce GUT theory, and then we'll discuss about some predictions of GUT, like proton decay and topological defects. In the next part, we'll discuss about phase transition in the early universe cosmology, and then inflation and evolution of monopoles in an inflationary universe. Then we'll discuss about the evolution of cosmic strings and production of gravitational. Finally, then we'll talk about a scenario where cosmic strings are not stable, it's quasi-stable. And finally, I'll summarize my talk. So let me start with the standard model and its field contents, by mentioning the quantum numbers of the field. So quarks are fundamental under SU3C. So here is the gauge symmetry of standard model, which is SU12 cross U1Y, and a strong sector, which is described by the SU3 gauge symmetry. So you can see their quantum numbers. So the particle contents are under transform as a fundamental representations, or maybe a singlet. Sorry, smooth. And the gauge bosons are transformed as a real representation under the gauge symmetry. So so the particle multiplets have some hypercharge, which is quite arbitrary, in a sense that this U1 is not compact. So the basic idea in a grand unified theory is that the standard model gauge symmetry is a low energy artifact of a unified theory at a very high energy. So in between them, there could be some intermediate gauge symmetry, and to break associated with some possible intermediate scales, and there will be some scalars whose vacuum expectation value will break some higher symmetry to its daughter lower symmetry. Now, here is the few example of GUTs. Like the lowest minimal GUT model is based on SU5, which has rank 4, which is same as the standard model gauge symmetry. So here the standard model fermions are embedded in two representation comprising of 5 bar plus 10. This combination actually cancels the anomalies in the theory, in the gauge theory. So this is SU1, so there will be anomaly, and that should be cancelled. Now next model comes from some higher symmetry, which is SO10, and SO10 is an anomaly free group, and however it has higher rank, one rank higher than the standard model gauge symmetry. And the standard model fermions comes from this 16-dimensional representation, which is the chiral representation under SO10, and this contains all the standard model fermions along with a singlet which behaves as a right-handed neutrino. And if we go some higher symmetry, we can embed this standard model into E6 exceptional symmetry of dimension 6, which has rank 6, and it has 27 dimensional representation that actually include the standard model fermions, right-handed neutrino, and along with some exotic fermions which are vector-like, and this is like Majorana type. So for the motivation, like as we know, the standard model gauge couplings tend to meet at some higher symmetry. So this could be a hint of a unified theory, but this could be also a coincidence also. However, this imposition of higher symmetry may constrain some free parameter of the standard model. As we know, there are 19 free parameter in standard model if we don't include the neutrino mass. And So, and another thing is all fermions, including a right-handed neutrino, can be put in one representation in GUT. And as in standard model, U1Y is is a non-compact group. So actually, if we embed it in a simple gauge symmetry, so actually it implies the charge quantization which is observed in the nature. So standard model itself cannot explain the charge quantization. However, the anomaly cancellation can impose a charge quantization in standard model. So next, hello.
Yes, we can hear you.
Okay, thanks. Thank you. So next we'll discuss about the predictions of GUT, which are proton decay and topological defects. So proton mediation of leptocore. So there are leptocore gauge bosons in standard in grand unified theories, which actually can leads to proton decay into meson plus some anti-lepton. For an example, there is a leptocore gauge bosons which transform as this, so which has a fractional charge, and this could give rise to this leptocore vertex and this dicore vertex, and these two vertex gives rise to this process at the fundamental level, which gives rise to at the pattern level, which gives rise to proton decay into pi plus and a anti-neutrino. And this proton decay channels actually follows this selections rule. Now this proton now Superkamiokande experiment has pushed the proton lifetime bound beyond 10 to the power 34 years, which in turn constrains the unification scale to be roughly above 5 times 10 to the power 15 GeV. So, and this constant actually rules out many non-supersymmetric grand unified theories in their simplified form. So in this talk, we'll mostly follow the non-supersymmetric GUTs. So supersymmetric GUTs are quite easy. So all the three couplings actually unified at around 2 times 10 to the 16 GeV. So these are quite safe from the proton decay lifetime bound and other things. So we mostly follow the non-supersymmetric GUT in this talk. So there are way outs, so threshold corrections and dimension 5 operators. So in our work, we have thoroughly analyzed all the breaking chains starting from E6 and SO10 through 1 and 2 intermediate steps with the left-right symmetry at least one intermediate stage. So here the notation is like the subscript of calligraphy G actually refers to the gauge symmetry. Like here, this subscript 3L, 3R, 3C actually refers to the gauge symmetry SU3C cross SU3L cross SU3R cross SU3C. And these are the fermion scalar representations, which actually is chosen by extended survival hypothesis, which says that only those, this is a prescription to choose the minimal scalar sector, which tells that only those scalar will be light in at some gauge symmetry, though which actually breaks that symmetry and any subsequent symmetry, and other scalar multipliers should be decoupled. Hello?
Yes, we can hear.
Oh, okay, thanks. Thank you. So the threshold correction comes into play when we break a higher symmetry and match that symmetry to its daughter symmetry at the breaking scale. So like here alpha denote the gauge couplings, here D denotes the daughter symmetry. So this equation gives the matching condition at the breaking scale, and there is a factor which actually depends on the masses of the heavy vector, heavy fermion, and heavy scalar along with the breaking scale. So this actually can alter the running of the coupling and can actually change the unification and intermediate scales. So we parameterize the threshold correction as the ratio of the masses of heavy scalars or fermion to the masses of heavy vector boson, and we assume that the vector boson is degenerate with the breaking scale. And we maximize the proton lifetime for this golden channel for two choices of R within half and 2 and 1/10 and 10. So with this choice, so we have analyzed all the one intermediate and two intermediate breaking chains, and we see how this threshold correction can improve the proton lifetime. So here we have plotted the intermediate stage. So the thing is that the GUT symmetry is broken at unified scale. Then there is an intermediate symmetry like SU2 or cross SU2 cross SU4, like Patisala with intact D parity and with broken D parity, and like left asymmetry and some other possible higher symmetry group which could arise in E6 model. So here Mi is a scale where this intermediate symmetry actually broken to the standard model. And on the y-axis, we have plotted the proton lifetime. And as you can see, let's say for example, if we choose the breaking path of SO10 via SU2L cross SU2L cross SU4C with an intact D parity, this was actually ruled out by the proton lifetime bound. However, if we take a sufficient amount of threshold correction, this model actually can be revived and can satisfy the proton lifetime bound. Similarly, if we introduce another intermediate scale, so like here we break SO10 at some unification scale mu to this Patisalam group with an intact D parity, then it is broken to the left symmetry group at some scale M2, and then at some scale M1, and then at M2 it is broken to the standard model. Now we plot M2, and on the y1 axis we have plotted the unification scale Mx, and in first intermediate scale, like where this group is broken, this Patisalam group is broken to the left symmetry group. And in the y2 axis we have plotted the proton lifetime. So as you can see, this if we don't take any threshold corrections, like all the heavy multiplets are degenerate with the breaking scale. So this model is actually ruled out. But if we take a small amount of threshold correction, actually this could be actually revived. This model could be revived. Now, since the unification scale is few order below the Planck scale, and if we assume that the unified theory is an effective theory of some quantum gravity or so we could expect that there will be some effect of gravity in the form of higher dimensional operator. So like this dimension 5 operator. Here f mu nu are the field tensor for the unified theory, and phi d is the scalar that breaks the unified symmetry. So this actually modifies the unification scenario, like these equations. And so here delta I actually depends on the intermediate gauge symmetry. This comes from group theory and thus direction of the wave. And this could only arise if this actually this symmetry breaking scalar actually fall in the symmetric product of two adjoint, because this field tensor always transform as an adjoint representation or real representation under the group. So and if and we can see that this actually can improve the unification and can actually revive the GUT breaking chains from the proton lifetime bound. So as we see, from this comparative study, that although proton decay is a smoking gun signal of a grand unified theory, so actually there are the breaking chains could be actually alleviate that current exclusion limit if we include some effect of threshold correction and dimension 5 high dimension operator. Now, next another.
Can I ask one question before you go? This going back to the previous slide, when you have this R equal 1, and you said that if all the scalars are degenerated with the scale, then that is what you should expect. But then in order to increase that ratio, it's not really a free parameter of the theory, right? Because in principle, you should get some mass terms that are compatible with your symmetry. So the question then is I mean, can you really justify this R to be different from very different from 1, let's say?
Yeah, it's not very different. You know, it's just half and 2, so it's not very different from the breaking scale. So in principle, you need to analyze the complete the potential, and you have to tweak the couplings to get the masses of scalars and heavy scalars and heavy gauge bosons and other things. So heavy gauge bosons are will be out of the G times V. So we have taken that they should be like at the same scale, and the scalars evolve around them. So the scalar will contains the quartic coupling and other things. So yeah, you can adjust those things like.
Okay. Thank you.
Yeah, anyway, it is non-supersymmetric theory, and yeah, so it is there is a naturalness problem, obviously. So that we can't get away, so we have to find things. So anyway.
Yeah, thank you.
Yeah, thank you. So here there comes the next prediction of grand unified theories, which is topological defect. So basically topological by prediction of topological defect, actually we can look into the topology of the symmetry. So till now what happens, so from the particle content we guess we can go, so from a proton decay we can guess that there may be some gauge boson, massive gauge bosons, which could come from the SO10 group. But from the analysis of the topological defect, so you can actually prove the topology of the symmetry. So it's quite it is in a sense complementary to the proton decay, which can actually gives the hint of a unified theory. So topological defect may arise during the spontaneous symmetry breaking of a higher symmetry group down to its subgroup. So mathematically, a non-trivial homotopy group of the vacuum manifold implies the formation of topological defects. So for different value of the homotopy group. So if it is 0-dimensional, so it will be domain walls. 1-dimensional, it is cosmic strings, and 2-dimensional, it is monopoles, and there are various hybrid defects also can be formed. So we have analyzed all possible decays, all possible breaking paths, and have tabulated all possible topological defects. So here you can see, so for most all the chains there will be monopoles, stable monopoles, which should be inflated away. So inflation should come into the play, and there were stable strings, and these stable strings can actually either, if they are inflated, so they will be inflated, and if they remains in the universe, so they can decay via radiation of gravitational waves, and also they can decay via radiation of other things like other particles also, but that's a different thing. So in our talk, we'll mostly focus on the radiation of gravitational wave from the cosmic strings. Now, this topological defect gives rise to various constant on the unified theories. Like there is a upper bound on the monopole number density from macro experiment, which is 10 to minus 27, and also Parkes pulsar time array puts a constant on the undiluted cosmic string, which is less than 10 to the minus 11 eV, which in turn constant the scale producing the strings to be around 5 times 10 to the power 13 GeV or so. So there are way out, which is inflation. So inflation has important impact on the spectrum of gravitational wave or also the co-moving number density of monopoles. Now, so as we are in a GUT theory, so we employ the GUT inflation, famous GUT inflation proposed by Safia and Vilenkin.
May I ask some simple question?
Yes, yes.
So as for the defects, are they all BPS defects or not necessarily?
Not necessarily BPS defects.
Sommerfeld, right?
Yeah, BPS, I mean the quartic couplings equals to the G square, like.
So I mean the multi-defects energy, is it simply the charge times the single charge object, or whether in the case of monopole, whether between two monopoles, whether there is any interaction or they are non-interacting, or whether it depends on the model.
Yeah, depend on the model. So here it's mostly comes like it is extended structure. It is not direct kind of monopole. This is ad-hoc polyhedral monopole.
I mean,
right?
Sure, but in the usual standard model case, I guess it can be easily made to be BPS. So the magnetic between two magnetic monopoles, the repulsion by exchanging the gauge boson can be cancelled by the attractive force by exchanging of scalars, right? My question is whether it is genetic in your SO10 model, or still it depends on the parameters, and only for very special choice of parameters whether you can realize that.
Yeah, it depends on how these are formed. So here whatever I have listed, they are mostly stable monopoles. So I think they are stable. So there is no gate interaction. So if sometimes the monopoles are connected by depending on the topology, they are topologically stable. So they are stable monopole. Yeah.
Yeah, but actually that was not my question. But anyway, you can go ahead.
BP. So okay.
My question was actually, I mean, not the stability, but whether it is really saturating the BPS bounds or not. Or in other words, whether there is some interaction energy or not. That part. Okay, maybe you can go ahead.
Okay. Yeah, actually I can. So yeah, it's like the monopoles we can include in our Maxwell equation. So it has a 1/r interaction or so. Yeah, so maybe. Hello.
Okay. Yeah. Okay.
So it has topological charge, which is like which are actually monopole charge, not like electric. Okay. So we employ we employ inflation driven by the Coleman-Weinberg potential of a GUT-singlet. So it was suggested by Safi and Vilenkin about 30 years ago. So now recent data, bicep cake data 18, and actually rules out this model by 2 sigma. So here is the prediction of this Coleman-Weinberg potential, while there is minimal coupling to gravity, and this is the prediction if it is like WR is the effective parameter after inflation. So if it is matter dominated, this is the prediction, and this is if this is instant reheating or the radiation dominated. So it's like this, it follows like this. However, if we include a non-minimal coupling to gravity of the scalar, actually we can revive this model. So as it happens for most of the models. So yeah. Any question?
How does it alter specifically the potential, the Coleman-Weinberg potential, the inclusion of this non-minimal coupling to gravity?
Yeah. So if we include this non-minimal coupling to gravity, so the effect actually potential shape changes. So it become more slower. So that is why it gives less R value and other thing.
But is it the term that you wrote there, like 1 plus C and then phi square minus m square over R?
Yes, this is the coupling.
Okay. Mhm.
This coupling R is the richest scalar.
Mhm.
So the tension is at which level? 95%? Without the coupling, without the minimum coupling. No minimum coupling. With a minimum coupling, there is a tension at which level?
I think he mentioned 2 sigma, so
2 sigma. This is 2 sigma. This is my question.
Mhm. So 2 sigma.
Okay. So, is there any question?
No, I think we figured it out. Thank you.
So, I mean, the question just in the previous one here by the non-minimal coupling, then the PK18 plus BAO plus Planck 18 data, does it then is it consistent with the current data by choice of the psi value? Or, so that's what you are saying, right?
Yeah. The choice of psi value. So yeah, it depends on the psi value. So it's sorry. So for psi of the order of 10 to the minus 3, actually,
okay.
yeah. And if we include a singlet, basically the coupling of this phi square, chi square, here chi square is the the scalar which breaks the symmetries. Actually, this brings about the inflation below the wave. So basically, inflaton rolls to its minima, which from 0 value to its higher value, and as it rolls down, basically this coupling gives rise to spontaneous symmetry breaking at some intermediate scale. So okay, I think I missed one slide. Okay, sorry. Okay, so now here is the evolution of the intermediate mass monopoles. So this, so here this xi is different from the previous xi. Sorry for the confusion. Sorry. So this xi is the basically correlation length, which is given by the inverse of the Hubble parameter or the effective mass of the scalars that actually breaks the symmetry. So the initial number density of the monopoles will be given by this. So basically, we assume there is one monopoles at a correlated region, which will be actually diluted during the inflation by this factor. Here, Nm is the number of e-foldings suffered by the monopoles. Then it will be further diluted if there is a inflaton oscillation, and during inflaton oscillation, it is basically matter dominated universe. So, and so this whole factor gives the number density after the reheating, and if we divide it by the entropy density, we will get the co-moving number density, so called the yield. So, and the macro gives a upper bound on the monopole yield, which is to be 10 to the minus 27. We adopt a threshold for observability that monopole should be greater than 10 to the minus 35 number density, so that it could be observed in some future experiment. So with this bound, so we can see if the monopole suffers around 11 e-foldings, they can actually elevate the macro bound. And for the threshold for observability, they can suffer up to 17 e-folding. So this is important because if we want to observe some gravitational wave from cosmic strings, so we can see that there are many breaking chains which actually produce stable monopoles and cosmic strings at the same breaking scale. So if we want monopoles to be inflated, so then the cosmic strings will also be inflated. So as we can see that monopole actually can only 11 e-foldings could be sufficient to dilute the monopole sufficiently so that it can satisfy the present bound. And this number of cosmic strings, but the cosmic strings could suffer till 50 foldings. Actually, we'll see later. So that's the thing. Now the cosmic string interstring distance will be like the interstring separation during production will be given by this factor. So here again, xi is the correlation length, which will be given by the minimum, we assume, minimum of the Hubble radius or the correlation length of the scalar that breaks the symmetry, which will be further expanded during inflation by this factor, and this factor after inflation, and this is this factor after the reheating. Now the strings can actually re-enter the post-inflationary horizon after a cosmic time if this string separation become the particle horizon at that time, which will be given by which will be order of the time or the order of the time scale. Now, so now if they re-enter the horizon, they can intercommute and form loops, and they can actually decay via the emission of the gravitational wave. So the frequency of the normal mode of any case, so we can actually break it in normal modes, and the frequency will be given by this formula. So here is the case the number of the mode, and this is the length of the of the loop at the time of the emission of the gravitational wave t tilde, and ti is the formation of the loop time, and this is the rate shift that actually this frequency will suffer. So this is the initial frequency which will be rate shifted by this amount. So here is the plot. So I have taken from this paper. So there are three parts in the spectrum mostly. So first thing is the string loops that actually produce and decay during the radiation dominated universe. So that gives rise to this scale invariant spectrum at the higher frequency, because here the loop size will be small. So the smaller loop size, small loop will contribute to the higher frequencies. As we can see this, so this is loop size. So as the loop size gets smaller, it actually contributes to the higher frequency. And this orange part actually describes the gravitational spectra coming from the loops that actually produced during the radiation dominated universe and decay during the matter dominated universe. And this small part basically describes the loops that actually forms and decay during the matter dominated universe. So altogether we get this kind of spectra. Okay, so here is the observational prospects of gravitational wave from the cosmic string. So if the cosmic string doesn't suffer any inflation, so they are present from very early universe, let's say 10 to the minus 20 seconds or so. So there could be a range of the breaking scale corresponding to 10 to the minus 11 to 10 to the minus 20 could be actually observed in various proposed experiments. This actually corresponds to the breaking scale till 10, starting from 10 to the power 9 to 10 to the power 13 GeV. And here is a provisional signal from nanograph data, so which actually gives a hint of a gravitational background coming from a cosmic strings of string tension around 10 to the minus 10, which corresponds to a symmetry breaking around 10 to the 14 GeV or so. Now if the string suffers some inflation, so they re-enter the horizon at a late time, so therefore the small loops will be absent there. So basically loop length actually is proportional to the horizons, particle horizon size at the time of the their formation. So basically small loop will be absent, so the spectrum at the higher frequency will be diminished. So here you can see these are the spectra when they doesn't suffer any inflation, and these are the spectra when they suffer some inflation and re-enter the horizon at some late universe. So the frequency in the higher frequency range will be faded, and they can actually satisfy the PPTA bound. Okay, so here is a more larger plot of that. So yeah, from 10 to the minus 20 to 10 to the power minus 11 could be observed, and even 10 to the minus 10. This value actually is 10 to the minus 10 and 10 to the minus still 10 to the minus 9 is allowable in GUT inflation scenario. Hello?
Yes, we can hear you. Yeah, we can hear you.
Okay, thank you. So there was as I have said, that mentioned that there was a provisional indication of a gravitational background from nanograph data, and also later it was like similar findings are found from IPTA and also PPTA, also from PPTA. So these are their contours. So if we see if there was no inflation, so cosmic strings starting from 10 to the minus 11 to 10 to the minus 10 string tension can satisfy this nanograph finding. However, if they suffer some inflation, they can still explain that finding. So here alpha string actually basically the quartic coupling of the scalar that breaks the symmetry, and G is the gauge coupling. So in our work, so we have shown that this can actually still the strings in a GUT inflation can still satisfy the nanograph data. So here this blue line actually shows the minimal TF. TF is the horizon re-entry time that actually is necessary from PPTA to satisfy by the PPTA bound. And here this brown dash dot line corresponds to the horizon re-entry of different of the strings depending on the ratio of this coupling. Here alpha STR is the like quartic coupling of the scalar that breaks the symmetry, and G square is G is the gauge coupling that gives the that correspond to that U1 generator that actually is broken at that with the wave of this scale.
Sorry, one question. Is that a completely free parameter, or can you fix it from the inflationary observables?
This is a free parameter. This is a free parameter, but from the naturalness side, that if the scalar is degenerate with the gauge bosons, then it should be of the order of 1. Okay, because the scalar mass will be proportional to the square root of this, and the vector mass will be proportional to G. So this should be order 1.
Thank you.
Yeah. Okay. Next, we'll study the discuss the quasi-stable cosmic string. Now consider a breaking where SO10 is broken to Patisalam at some GUT scale, then it is further broken to this SU, this left symmetric model, and then further it is broken to the standard model. Now, if there is no remnant Z2 symmetry, now there will be string will be formed at during this breaking at M2, and there will be monopole at the breaking at the M1. And topologically, these monopoles actually, this monopole and anti-monopole generated at this M1 scale actually will be get connected by the cosmic strings formed at this scale. Now, this hybrid defects actually are topologically unstable, and their decay width is given by this formula. So they depends on the scale where the monopoles are created, and the scale where the strings are created. So basically, so here the string tension, mu is the string tension, which is of the order of pi times the breaking scale, and is a mm is a monopole mass, which is of the order of the breaking scale, 10 times the breaking scale. So thus although the strings are topologically unstable, they are actually stable if this ratio, the separation of the two breaking scale so becomes greater than or equals to or 8.7, which basically says if the two breaking scale are like separated by a order or so, magnitude of by one order of magnitude or so. So but the point is that this monopole and anti-monopole connected by the strings can decay by radiation of gravitational or via their gauge interaction by unconfined fluxes. So in our scenario, like these monopoles are formed prior to the strings. So we assume that these monopoles are actually partially inflated. And so they partially inflated and can re-enter the horizon at late time. Now, so as they are partially inflated, the strings generated at the second intermediate scale actually makes random walks with the step of the order of the particle horizon size, and they can actually intercommute and form loops and decay into gravitational waves like a stable cosmic strings. But as the monopoles and anti-monopole re-enter the horizon, so there will be monopole, anti-monopole connected by the strings, which can actually decay into gravitational, or via they can only just decay via gauge interaction. So basically what we can get, so after monopole and anti-monopole re-entering, after the re-entrance of monopole and anti-monopole, there will be no further loops. So the gravitational waves from the loops will be absent, and those loops would have been larger loops at late time. So that in that sense, that larger loops will be absent. So absence of larger loops mean there the gravitational waves at the lower frequency will be faded or absent. So basically, we can actually alleviate the PPT bound from in this scenario. So you can see. So here, like this or the scenario if there was only stable string. Now, if the strings are connected by monopole and anti-monopole, and this monopole anti-monopole pair re-enter the horizon around 1 second, so this lower frequency region will be faded completely. And instead of this, so we'll get a frequency spectrum which actually which has some this lower part absent. So this frequency will be actually probed by LISA and other observatory, but cannot obey the PPT bound. So this would contain mostly two parts, like the loops before the loops decays before the monopole anti-monopole enters, and loops that are remnant after the monopole anti-monopole enters, and the contribution coming from monopole anti-monopole connected by the strings. Hello.
Yes, yes, we can hear.
Okay, as a summary, so many non-supersymmetric grand unified theories are incompatible with the superchemical and the proton lifetime bound unless we take the threshold correction and the effect of high dimensional operator into account. So they can improve and can alleviate the bound. Now, topological defects like monopoles, domain walls conflict the cosmological observations unless they are inflated. And from the macro experiment, so we can get a bound on the intermediate scale, which should be above 10 to the power 13 GB from the monopole number density point of view. Now, now this inflation can elevate the PPTA bound as we have discussed. So, and a range of cosmic strings with string tension from 10 to the minus 10 to 10 to the minus 20 will be probed by various experiments, and the quasi-stable strings can produce a observable gravitational and satisfy the PPTA bound. So, okay, thank you. So, any question?
Yeah. Any question?
Okay, I have a question.
Yeah.
Okay,
Yes,
so
please.
you introduce many defects, domain wall, strings, and the monopoles, right?
Yeah.
And you showed mainly the strings, or the strings at the end, the monopole and the anti-monopole is attached. Also it's basically strings that you showed. So how to get the limit to the parameters once they are very inflated, so far away, so they are out of the horizon, then re-enter into the horizon later stage, then
Yes.
the decay into gravitational wave, right?
Yes.
So
yes.
what if you do the similar analysis to the magnetic monopoles and the domain walls?
For a domain wall, the thing is like it's quite tricky. So domain wall, if they re-enter the horizon, they will start dominating. So that's the main problem with domain wall. So there is no still viable answer to that. So people are trying.
Okay, so may I repeat? So in other words, what you are saying is that the presence of domain wall will be very inconsistent with the observation. Is that what you are saying? Because
Yes. If it is stable domain wall, yeah.
Okay, and
So
then how about the magnetic monopole?
The magnetic monopoles actually, so they could be in the like horizon. There is a bound on the number density, upper bound on the number density from the non-observation of that monopole. So there is a Parker's limit also. So they could be in the horizon,
So
but they are not yet detected.
Right. So the from that non-observation, so how those data are converted into the parameter range? Like I mean, you analyze the decay of the strings and then put the limit for the G times mu parameter, right?
Yes.
So here the constant is to what in the theory? So here
In
you
the
show
theory,
the monopole.
Yeah, it's mostly on the intermediate scale. So the GUT monopoles, in the GUT symmetry, there will be also monopoles, but that should be actually inflated. And the inflation scale, okay, sorry. Hello?
So let's say, so what you're saying is that this one will put some limit on the magnetic monopole formation scale. In other words, magnetic monopole mass, or
magnetic monopoles, yeah, magnetic monopoles formation scale. I don't mean the mass. So yeah, it depends on the intermediate scale. Basically, what here the main thing is the number density of magnetic monopoles. The intermediate scale magnetic monopole. Yeah.
Right. By intermediate scale, what you mean by that is the symmetry breaking scale.
Symmetry breaking scale, yes.
And that symmetry breaking scale may be related to the monopole mass or not. Is it
Yes,
totally
that is
independent?
related proportional to the monopole mass, and there was
So there I'm expecting that then if this non-observation gives some restriction or limit to the intermediate scale, it may be converted into some parameters of your theory, for example, the intermediate scale mass or monopole mass like that. So since you have not shown those data, unlike the string decay case, that's why I'm asking.
yes, actually there was a calculation by Kolb-Turner. So basically, so there is a calculation on the velocity of the intermediate scale monopole. So that actually is valid for 10 to the power 30, 10 to the 14, or even 10 to the 15 GeV monopoles. So that is around, I think, 3 times 10 to the minus 3 times the velocity of light. So using that value, actually we can get the monopole flux. The macro bound is actually on the monopole flux. That is their number density times velocity divided by the solid angle 4 pi. So
Okay.
yeah, so from
Okay.
that thing we actually converted it to the monopole yield, and basically that
Yeah,
constant.
those have been done by others already. That's what you
Yes, yes,
also
yes.
say. Okay. Okay,
Yes,
thank you.
and okay, and from the requirement that the monopole should suffer some sufficient amount of the e-foldings, actually that gives rise to a constant on the intermediate. So actually I miss one plot. So here is the Kibble mechanism. So by Kibble mechanism you can actually determine the scale of the symmetry breaking scale and associated with the here you can see the symmetry breaking scale, sorry, associated with the breaking scale that actually suffers this number of e-folding. So any symmetry for topological defects formed at this scale, like around 10 to the 13 GeV, actually suffers this amount of e-foldings there in GUT inflation scenario.
Okay, thank you.
So one more question. Do you have a motivation for this non-minimal coupling to gravity?
The motivation is to satisfy the present data.
Mhm.
So the minimal coupling was still valid till Planck 2018 data, but the recent data actually rules it out by 2 sigma, as you can see. So we have to include the non-minimal coupling. The small value of non-minimal coupling actually can give rise to a good agreement with the data.
Yeah. No, I asked because, for example, you couple this inflaton to this non-minimal to gravity. So if you think to extend these theories to include matter, for example, there may be some non-trivial also coupling to matter. So then you could have more observable consequences of that, coupling to gravity. So that is why I ask. But yeah.
Matter means other scalars that breaks the symmetry.
Yes.
Yeah, so there may be, but as you know, so there is a hierarchy in the scale. So start from the electric scale to Grand Unification theory scale, and here we have taken a small non-minimal coupling. So we can actually safely ignore that consequences. So.
Or have you thought of another potential beyond this Coleman-Weinberg in order to have inflation in this kind of non-supersymmetric models? Or is it really the only one that works?
No. I think other possibilities also work. So that there could be other possibilities also. This is the simplest version. Like if you take some quartic coupling and just take the It's quantum version of the potential. So,
Yeah, okay. I don't know if you have more questions in the audience. No? Okay, so now, if we can thank him again, we can thank you again. Thank you very much.
yeah, thank you.
We enjoyed your seminar, so I hope you can send us the slides. And yeah, if we have more questions, we can probably ask you directly. Yeah, can you hear us?
Yeah, I can.
Oh, okay, yeah, it's just, okay, now we see you. It's just because we cannot see your on our screen, but now I see you. Okay, so are we finished? Huh? Okay. Yeah, thanks a lot then.
Yeah, thank you.
Nice to meet you.
Yeah, thank you. See you.
Bye, thank you.
Bye.